Hi there. In this section, we look at optimizing. Remember, optimizing or optimum means best for a particular situation. So that could be, maximum, could be minimum, depending on what's best for the scenario. So if you were looking at a profit function, then certainly a maximum is good. If you're looking at a cost function, certainly a minimum is the direction to go. And we're going to be doing this even more blindly than before. When you did this in single variable calculus, you could kind of cheat a little bit and look at a graph on a graphing calculator. Good luck with that here. That would be terribly difficult since your TI-84 does not graph in 3 dimensions. So we're going to be more heavily dependent on the mathematics. But before we get into it, I want you to know what you're looking for and at least have the visual in your head. This is the best function I could come up with and the best view that makes it easy to see what's what. So hopefully this view is good. So you can read the definitions here. They're the same as before. An absolute maximum is going to be absolutely the highest point on the surface. So that's that there. Imagine there's kind of a tangent plane there. So the derivatives with respect to both x and y are going to be 0 there. We have other peaks where we're concave down, but we're not the absolute maximum. So another place where slope is probably 0 for both x and y, and we have relative or local maximums. So just like in single variable, something like this, you would have an absolute maximum here, and here you'd have a local. So the 3-dimensional version is pretty much just an analog. Likewise here, we have local mins and absolute minimums. So if you had something like this, then of course this is an absolute minimum, this is a local or relative minimum. Okay, so the idea in single variable is you could get away with just using the first derivative to find out where you change from increasing to decreasing. The problem we have here is you have 2 directions, x and y, with which that could happen. So we jump straight to a second derivative test that will actually look at concavity in both directions. So we'll be looking for where we're cupped upward for minimums and cupped downward for maximums. Okay, so those are the points of interest for us. Hopefully we don't deal too many functions or surfaces that are this complicated. I do have the, it's not all going to quite fit, almost. Let's go a little bit. I do have the the contour map or level curves here. So you should be able to pick out what's what. Here is your absolute minimum. Absolute because here we're only at like -5, here we're -10 or somewhere around there. So you can kind of see how this compares to what we have up there. So this is your local or relative minimum. And then similarly over here, we have a couple values. This is a local max, and this is your absolute maximum. Based on the picture, it's probably around 10 or maybe a little over. Kind of looks like that in the surface. If you look above, that the high is at about 10 here, and the low is also at 10. Kind of hard to tell since we're looking at it in the picture. You can tell we're kind of looking at it from above a little bit. So this is where the level curves can help you get an idea of what's going on. So these are the points we're after, and we're certainly not going to do it graphically. That would be quite difficult. About the only things we'd be able to work with would be, the upper or lower half of a sphere or a paraboloid or something. But when there's more than just one of these things occurring in a surface, it's pretty complicated. So on the next page, I will show you what's called the second derivative test, and you'll see how we go about finding these. Actually, that's in 2 pages. Before we get to that, we're going to look at critical values, or in this case, it'll be critical points. So let's move on to page 17.